Okay, well, good morning. This is really indeed an MNT-SIG presentation. It was an outflow of the work we have done inside the MNT-SIG for the last, 2 years at least. So Bill is the MNT-SIG leader, Michael and I are active members in the MNT-SIG, and Michel is of course always there. And as Michael already mentioned, Mark Steinman has of course told us that everything we were doing was wrong and we need to do it differently, which was true, he's right. So we did it differently. Okay, so let's start with the argument that we're probably all familiar with when it comes to multithreading, and that is that on a computer chip the transistor count roughly doubles every year, which was observed by Moore some time ago, and it still holds today because what you see here is the processors listed until 2020, and that used to mean that a computer chip was essentially becoming twice as fast every year. And that means that you can just enjoy that. If you're writing software, there's nothing you really need to change to your software to enjoy that extra speed, other than perhaps compile with a more modern compiler that takes into account particular new processor optimizations. But this is no longer the case. This image has been taken from Computer Magazine, and this clearly shows that double the transistor count does not translate to double the speed on a single core anymore. It essentially translates to double the cores. So there are some reasons for that. The instruction level parallelism progress has stalled since 1990. You can check that on Wiki. I'm not going to explain. It turns out also that parallel computing uses less energy than faster computing. Essentially, if you take 2 bits that flip at a certain rate, compared to 1 bit that flips at double the rate, the 1 bit that flips at double the rate is just using more energy and therefore also producing more heat. And getting rid of heat in computer chips is of course one of the bigger challenges at the moment. So transistors are usually made by cutting circuits out with light, and that light has a certain wavelength, and we cannot make the wavelength of that shorter anymore. So we are limited by the distance at which we can actually make such cuts, and this makes that we cannot really make transistors much smaller anymore, which means that power has to be transferred over a certain finite distance that we cannot make smaller anymore either, which means we cannot reduce the latency anymore. So the internal speed of a chip is not getting much faster for that reason as well. Then there is a technology called hyperthreading, on which a single core can already run multiple threads parallel. It can process 2 threads at the same time in part. And as we could see on the previous slides, any computer now has multiple cores to begin with. So a single process can use those multiple cores by concurrently running multiple threads that execute at the same time at different processors. But this of course requires a bit of change in how you write your software. You can no longer just do all your computations in 1 thread. You need to now do them in multiple threads and make sure that those threads synchronize with each other properly. So that is what we're talking about today. So that brings me to the outline of the presentation. First, I need to demonstrate that CAPE-OPEN interoperability is not stateless, and this is important for understanding how threading has worked so far and how it should work. And I will comment on how it has worked so far in the current ecosystem of PMCs, after I do a little bit of explaining on how COM threading models work. And I will then also comment on what has not been going right with that, which causes a bit of slowdown in some cases. Then of course we move on to COBIA. We decide that we learned from COM and how we should do it better in COBIA. But one of the design criteria of COBIA is of course that it needs to one-on-one operate with COM, so the interoperability between COM and COBIA will also be discussed. And finally we move on to some recommendations and the outlook. So let's start with the state part. Here you see the interaction between a PME and a Property Package Bmc on which a flash is calculated. This works by the PME setting a context material on the property package. The PME then sets the temperature, pressure and composition, for example, on the material context, and then it calls the property package again with the request to perform phase equilibrium. The property package will then get the temperature, pressure and composition from the context material. It does internally do the flash calculation, and the flash results, the phases, the compositions, phase fractions, etc. are written to the context material, and then the call returns finally. and the PME can obtain the phase equilibrium results from the material that it set on the property package in the first place. So now imagine that there is two PME threads and they both operate on one property package. The second PME thread would pretty much be doing the same thing. It would set the contact material as the first step of the phase equilibrium calculation on the property package, and it doesn't take a lot of imagination to see that that will go horribly wrong, because the property package that was in the process of doing a phase equilibrium on thread 1 is now suddenly seeing a different context material. So that is presuming that setting the context material itself didn't cause a race condition, because it might have been doing that from two threads concurrently as well. So that means that essentially the entire block in green here, which involves multiple calls from the PME to the PMC, must be shielded somehow. This cannot be done by the property package, because the property package is not in control of this entire sequence. It receives several calls during the sequence, so this synchronization has to be done by the PME over the entire part where the state must be maintained. And it doesn't have to be done from one thread. All the stuff that is currently done here in the green block can be done from multiple threads, as long as the PME synchronizes those actions in some meaningful way. And then the other action on the property package, such as happening from thread 2, will simply have to wait until that entire interaction is completed. So the state on the property package, as shown in the previous slide, is a result mostly of the context material object. For unit operations, the story is similar. Unit operations have ports, and the ports connect to materials. And if you would connect different materials from different threads, surely the unit operation would not be able to do consistently the calculations on the set of materials that you specified from the first thread. All PMCs have an additional piece of state, which is the simulation context, which would be accessed in a concurrent manner, which is not pleasant. But also, even if we would solve all of those state problems and pass the context material, for example, as an argument to each call, we still have the fact that property packages and unit operations, and every PMC for that matter, carries a configuration. And this configuration also needs to be synchronized. For a unit operation, for example, you do not want to be editing the unit operation in one thread while you're calculating it in the other thread, and the same goes for a property package, of course. Now, we allow also every PMC to have parameters. For property packages, there are, as far as I know, no property packages out there that currently expose parameters publicly. But for unit operations, this is certainly the case. And changing parameters in a unit operation, of course, also changes the state. So trying to make a unit operation stateless would somehow involve also passing the parameter values, or at least the parameter values that are subject to change during the simulation at hand, as command line arguments to the actual calculation, which is all not that straightforward. And even if we manage to go in that direction, still some level of synchronization appears to be necessary from the PME side of things. Okay, this is all leading up to synchronization is necessary somehow, despite the choice of threading models. So let's talk about threading models for a bit. The common threading models are observed as somewhat complicated, so I will try to explain them. The things that are important to us at least, and I'll try to keep this briefly. Sorry if it gets a bit quick here. At the moment you start using COM at a particular thread, you need to initialize COM on that thread, and during that initialization you tell Windows, we're going to use this or that threading model at the thread. You really have two choices there. The thread is either a single threaded apartment, which means that all COM interactions will be constrained to the current thread, or the thread is part of the one and only multi-threaded apartment, which means that multiple threads may interact with each other over COM, and all the threads that are initialized as multi-threaded can take part in that apartment. So that is what the PME does to initialize the threading model on a particular thread, and it holds for all interactions at that thread. An in-process COM server, such as a PMC, in fact nearly all PMCs that are out there today, advertise their ability to do threading, and then they have the choice between 5 choices essentially, 5 options. The first option is apartment threaded, and apartment threaded means that the PMC must be called only on a single thread, which obviously then is the thread it was created in. This does not mean that there is only one thread. There could be multiple threads with multiple PMCs, each of which are constrained to their own thread. So still in the apartment threaded model, PMC implementations need to take care of a certain level of thread safety. But each object can only be accessed from one thread, so typically class variables are pretty safe from concurrent operations. Then there is free-threaded, and if you advertise yourself as free-threaded as a PMC, you're promising the PME, you can call me concurrently from multiple threads. That's what the common threading model says. Even though it doesn't necessarily make sense to do so, because as we have already seen, PMCs have a state, so calling them at the same time from different threads is not necessarily a useful thing to do. But that is what you promise to the PME if you advertise yourself as free-threaded. That also means that the PMC must live in the MTA apartment. It has no choice. So there's also the both threading model, and the both threading model is a promise to the PME that it can do either apartment or free. So it depends really on which thread you're creating the PMC. If you're creating the PMC in an STA thread, it will behave as apartment threaded. If you create the PMC in an MTA thread, it will behave as free threaded. And there are two more threading models. If you don't specify threading model at all, it ends up being single threaded, which means that all PMCs need to run from one given single thread. And there's also the neutral threading model, which means that all PMCs actually must be created from the one and only neutral thread that Windows will create for you. But please stay away from these threading models. Do yourself a favor. Do us all a favor. The PME initializes the threading model on a particular thread and then goes on to creating a PMC on that thread. And if the threading capabilities advertised by the PMC do not match the threading model that is initialized on the current thread by the PME, Windows will actually create the PMC for you in a different thread that is allocated by the Windows COM machinery, and will set up marshalling to that PMC for you, which means that because it lives in a different thread, the marshalling is actually pretty costly. Any call to the PMC will stop the current thread. The execution will continue on a different thread, which was waiting for your call to come in. Once the execution there is done, it signals to the original thread that it can resume, but everywhere there's waiting and synchronization involved, and those are just time-consuming things, so you want to avoid that where possible for performance. You can also run a PMC, you can also access a PMC from outside its apartment. But that requires two things. First of all, it requires marshalling. This is always done via marshalling. And it requires that the apartment that the PMC was created in also runs a message loop. Otherwise, your call simply won't be answered and you'll be stuck in a deadlock and waiting forever. So that was a little bit the story about COM threading models. And from there, I move on to the current status of multi-threading in CAPE-OPEN. Currently, of course, COM is the predominant middleware that is used. There are very few COBIA implementations out there, and we have a third middleware that's CORBA, but as far as I know, that has no commercial application of any volume. So CO-LaN has never identified publicly or documented that the state in which a PMC resides, the fact that it has a context material, that materials are connected to the ports, is an important problem in multi-threading, and therefore it hasn't really been clear how you should set up a PMC that can be accessed from multiple threads, because it has never been documented how you should take care of this synchronization. And perhaps because of this reason, pretty much all PMCs that are out there are advertised as apartment threaded. And that has some implications, and I will go over those implications, and I will try to sketch at the same time what the current situation is in some PMEs out there. So one option to get around the synchronization problem is do not share your PMC. The situation sketched here is that we start off with a single thread in which we have the Property Package Bmc from a couple of slides ago to begin with, and then we start some calculation threads number 2 and 3 in this case. And instead of sharing the property package from the first thread, we duplicate the property package from the first thread. But this is Of course, it needs to be a proper duplicate, it needs to have the same configuration. But as soon as it lives in the second thread as a property package, that will only be accessed from the second thread. There is no synchronization issues, and you can simply calculate away and use your threads at will. There are a couple of buts here, of course. To get a duplicate of the property package from your thread 1 in your thread 2 and 3, you can persist the property package in thread 1 and depersist the property package in threads 2 and threads 3. But these are potentially also expensive operations because these property packages are separate, unrelated instances at this point. They cannot share the configuration, they do not know that they exist. It would be a lot nicer if you could make a duplicate in a different thread pointing to the same underlying software, but we have no machinery for that currently. Also, if threads 1, 2 and 3 are not all single-threaded apartments, marshalling will take place for any apartment-threaded PMC. And remember that currently pretty much all PMCs are apartment-threaded. So the opposite also holds. If threads 1, 2 and 3 are all of the single-threaded apartment threading model, but the PMC is not, it is not apartment or both, then surely marshalling will also take place. So that leads to the big picture income. If you want to avoid marshalling, then somehow you must make sure that the PME and all the PMCs that run on the current thread need to agree on the threading model. And this is not an easy feat. So another option that we see in simulators out there is the use of the global interface table. So you start off again with your main thread, which in Windows is typically the windowing thread, which is therefore a single-threaded apartment by default. You have your PMC, your property package, for example, in the main thread, and then you start a calculation thread or maybe 2 calculation threads. And rather than putting a property package in each of those threads, you're putting the property package from the main thread in the global interface table, and via marshalling you can access them from threads 2 and threads 3 by making calls of them. But these calls will be marshaled, and these calls will be marshaled over the main thread, which means that they're executing in the windowing thread. So they're not only competing with each other, they're also competing with the execution of the windowing. And if a particular PMC makes a very lengthy operation, your windows will appear non-responsive. So of course this particular setup is a pretty unpleasant setup, not only from performance, but also from user experience. And any PME out there that implements this particular model might want to reconsider and perhaps implement the approach outlined in the previous slides, where each thread has its own PMC. Or maybe the approach outlined on the next slide, but then properly. So another approach that we see in PMEs that are out there is essentially there is one single calculation thread, and the application is essentially single-threaded, but the calculation thread is not actually the windowing thread. So in the calculation thread, the PMC, in this case again a property package, is alive, and from the main thread the user might want to configure the property package. So the main thread makes a call into the calculation thread to configure the PME. This call needs to be marshaled, but that's not really a big problem because this is not a time critical call. It's not doing calculations, so that's all fine. And you can even make that call over a process boundary because you can marshal come between applications. So you can actually separate your calculation application from your main windowing application in this manner fairly easily. But yeah, clearly this is a single-threaded approach, so maybe not that relevant for the future outlook that I'm trying to present here. But I'm presenting this scenario in any case because this particular scenario has some unintended side effects. If, again, the threading model imposed on the COM machinery and the threading model advertised by the property package do not match. Particularly what happens out there is that the calculation thread is actually initialized as a multi-threaded apartment, despite the fact that it's essentially a single-threaded application. And what happens then is that Windows will create the property package in its own thread, and marshalling will take place in every call to the property package. This kind of marshalling gives CAPE-OPEN the name of being slow, but this is of course not CAPE-OPEN's fault. This is simply a poor threading model choice in the application at hand. There are fortunately ways at which we can work around this particular situation, which I will come back to later on. Okay, so that was the COM threading models, and as may have become clear over the last couple of slides, The problem with the COM threading models is really that everybody needs to agree about the threading model. All the PMCs and the PME need to have a compatible threading model, or marshalling will occur. So we didn't want to do that in COBIA. So despite the fact that interop between COM and COBIA might not be optimal for now, we're keeping our eye in the future, and we say in the future this is what we think should be a proper threading approach, and we're decoupling the threading model from the thread. Instead, we are attaching a threading model to each individual interaction between a PMC and a PME. At the moment the PME creates a PMC, it is decided for that pair what the threading model will be, which means you can mix and match different threading models per thread, which is distinctly different from COM. So let's have a look at the threading models. There is the default COBIA threading model, and in the default COBIA threading model, the PME can access the PMC from any thread. It may, however, not make concurrent calls on the PMC. So this is different from the Windows free threading model. The Windows free threading model allows concurrent calls from different threads on the PMC. The default COBIA threading model does not. The PME must assure that it's not making two calls at the same time to the PMC. And in doing so, we've simplified severely the PMC authoring, because in the PMC you can safely assume that you will not get concurrent incoming calls on the same object or any of its secondary objects. The fact that you cannot make calls on any of its secondary objects is in fact obvious. So if you're, for example, calculating a unit operation in one thread and you think the port of a unit operation, which is a separate object, is not the same as the unit operation, so I can surely make a call on that. Well, clearly you do not want to disconnect the port of a unit operation from another thread while you're calculating the unit operation on one thread, so that is a no-go. Sometimes it's not that obvious. For example, you cannot read the value of a parameter on one thread while you're calculating the unit operation on another thread, because this may lead to a race condition, and part of the exercise here is that we want to make a threading model that is easy to author for PMC authors, and the PME needs to synchronize in any case, because the PMCs have a state. We have seen that in the first couple of slides. So if your PMC cannot comply with the default threading model, it can advertise a different threading model. This threading model is the restricted threading model. And the restricted threading model is very much like the apartment threaded COM threading model. This means that your PMC can only be accessed from one thread at the same time, which clearly then is the thread it was created in. The only reason that I can think off the top of my head that you want to advertise your PMC as a restricted threading model PMC is because internally it's actually using a COM object that is apartment threaded. Otherwise I would not see any particular reason to do that. And that's it. These are the COBIA threading models. There's only 2 of them, and you see them here. And typically I would expect most implementations to use the default threading model. So when a PME is actually creating a PMC, it can state its intention. If the PME says, I'm only going to use this particular PMC from the current thread, I will never access it from a different thread. It can indicate that during creation. It can indicate restricted threading is good enough. And then COBIA will create a PMC for you. And if it needs to create a restricted PMC and the PME has not said, I will use this only in a restricted manner, then clearly COBIA must put some action in between that will ensure the PMC is only called from a single thread, and it will marshal it, which will work very much along the lines of what COM does. It has its own thread pool to create PMCs in, and it will run the PMC from a dedicated thread. The other way around, that's not necessary as opposed to COM, because a default PMC will run fine in a restricted context. So we're already done with half of the threading scenarios just by defining only 2 threading models that are more compatible to each other. What I have not shown in this presentation, I realize now, is the threading model that applies when the PMC is making callbacks into the PME. I should have inserted a slide on that, but essentially the agreement for both COM and COBIA is that if a PMC gets called, it gets called on a PME thread, and it cannot call back any PME objects other than the thread it was being called from. So it is not safe under any circumstance for a PMC to create its own threads and to access, for example, a material object from that thread to do thermal calculations on that thread. The bigger picture is there. We want the PME to be in control of multi-threading, not each of the PMCs. The PME has a better idea of what needs to be done and how the load needs to be divided. And making a threading model that allows for multi-threaded callbacks into the PME is just much more complicated. So then we need to have a look at how COM and COBIA interact. If you're using COBIA PMCs in a COM environment, that actually works rather easily because the way we have defined the COBIA threading models. So if you're using COBIA restricted PMC, it is simply advertised to COM as apartment threaded and all your requirements are already immediately honored, because COM will only call that particular PMC on one single thread, which exactly matches the restricted threading model regulations. If a COBIA PMC is using the default threading model, it is advertised as both, which means that the scenario that I sketched earlier on with the single threaded different incompatible threading model scenarios is automatically solved because it is capable of running now in the same main PMC thread. So this is one of the solutions of the problem stated earlier. However, if a COM object is created as free-threaded, concurrent calls can come in at the COM object. So it must be a task for COBIA somehow to make sure that the underlying COBIA PMC is not receiving concurrent calls. So it must synchronize in this particular scenario, which is not any significant penalty in my view, because this synchronization will actually never really lead to locking, because for that concurrent calls actually do need to come in, and it doesn't make sense, as we have seen in the first couple of slides, because PMCs have a state. If we use a COM PMC in COBIA, we have to take a little bit more attention. Our first idea was to use co-initialize in a smart manner, and then Mark pointed out to us that it is not a good idea, because if you co-initialize from COBIA on a thread that has never been initialized by the PME itself, it doesn't mean that the PME is not going to co-initialize on that thread later on, and it might choose a threading model that COBIA did not choose and cause a conflict there. Not only that, but every call to co-initialize must be matched by a call to co-uninitialize. And if COBIA would call co-initialize on the current thread that was created by the PME, it never gets a chance to clean up. It gets notified of exiting the thread, but that's too late to clean up COM, and COM must be cleaned up. So it's really not an option either for COBIA to call co-initialize on a PME thread. However, COBIA can call co-initialize on its own threads. It knows when its own threads exit. It is never going to make a conflict with the PME COM initialization, which doesn't have direct access to these threads. So it can make its own thread pool for running COM objects and call co-initialize on there. The synchronization that was needed in the opposite scenario is not needed here, because the COBIA PME is using the default threading model in this approach, and it will not make concurrent calls on the PMC to begin with. Not to mention, in this case, the PMC would be a free-threaded object, and it should be ready for incoming calls to begin with. So that's not an issue in this particular scenario. So this is more or less the decision tree for creation of COM object from a COBIA PMC. First, it is checked whether COM is already initialized on the current thread as a single-threaded apartment threading model. If that is so, and the PME is requesting restricted threading for the particular PMC, then we just co-create instance. If the COM threading model is not compatible with the single-threaded thread that we're running at, COM marshalling will kick in as it would usually do. If the current thread is not COM initialized as STA, we check if it might be initialized as MTA. In that case, we always simply call co-create instance on the current thread, and COM will marshal if the COM PMC turns out to be single-threaded, apartment-threaded. So everything will be taken care of there by COM. So if the PME did not initialize COM at the current thread at all, which makes sense because it's a COBIA PME, then we are going to have to marshal, and we're going to have to run the COM PMC in a dedicated thread that is set up by the COBIA marshalling thread pool. which is of course is a disadvantage, because you would think in this scenario, if we call COM PMCs, then marshalling will essentially always take place. There is a way around that. If you're a COBIA Pme, you can initialize COM yourself just to prevent this problem, which is of course not charming if you're programming COBIA that you need to initialize COM. But it is really only a performance issue, and in the course of time we expect, we hope, these problems will fade out and everybody will either move to COBIA or make for a more threading, more pleasant threading implementation in the PMCs. So that brings me to the recommendations for Pme developers. If you're developing your Pme, make sure that the threading assumptions you made during development are actually reasonable ones, because as we have seen on the current status slides earlier in this presentation, sometimes they're not, and marshalling will essentially always occur. Also, if you're a Pme developer and you're making new developers, prepare for multi-threading. You probably don't want to do all your calculations on a single thread anymore. For PMC developers, if at all possible, use COBIA. COBIA will advertise default threaded COBIA PMCs as both, will take care of the synchronization for you, so using COBIA is just the easy way to go. If that is not possible and you need to stick with your COM PMCs, then you might avoid a bunch of marshalling issues if you go from your current apartment threaded implementation to a both threaded implementation. But then you must also make sure that your PMC is of course sufficiently thread safe, and you must avoid race conditions if you get concurrent calls. So that was it for my actually for the MNT6 recommendations. The outlook for the threading conclusions that we have drawn in the MNT6 is we have put them all in a note for the management board, so that the management board gets to make a decision on what to do next. Presumably this involves getting feedback from our community whether the selected threading model is viable and useful. We may or may not launch a request for comments on that. This has not yet been decided, but of course this presentation is also really a request for feedback. So if you have any comments on the threading situation, feel free to either comment now in the Q&A part or get in contact with us. We will continue to implement the COBIA interoperability, for which the marshalling part is already in place. We have demonstrated that last year, but we need to make sure that the threading model decisions are properly implemented. For example, the decision tree we saw a few slides back. It's not a lot of work, it's almost all there, and then we will publish work package 1, as Michael already presented in the previous presentation. And what I personally expect, this is my personal expectation, it is not necessarily a view of the MNT6, is that over time we'll gradually see a change in the current ecosystem where people move to COBIA essentially, or advertise their COM PMCs if they want to stick to COM as both. And the threading, marshalling delays will hopefully slowly fade out. That was it for me.